All right, for part B, as you see, we're going to revolve this green region about the line y equals 1. Here we go. This is y equals 1. Remember, this was f of x, and this was g of x. So blue is f, and purple is g, and the dashed line is the line that we're going to revolve the region around. So it's, in other words, axis of revolution. In the washer method, remember, we're using slices, or we're taking slices from the region perpendicular to the axis of revolution. So let me just show you my slices here. And you can choose different slices, it doesn't matter. Okay. So let's say like each slice comes with thickness dx. Okay. And this time, again, the revolution is about y equals 1 line. So let me just choose a representative or make a representative washer here. So essentially, after the revolution, so you will have something like this. And this comes with, obviously, thickness dx. Okay? So this is sort of like a punctured disk. Okay, so the center of that is right here. Okay, let me just show you what I got in a three-dimensional version of that, and this is in fact the region. Okay, and then obviously y equals 1 is right here. Okay. All right, so let's just revolve this around. Okay, so you see the inside part. So that inside part is sort of like this part is sort of like taken out, right? That's completely empty. So it's like a cone taken out of that whole three-dimensional object. And you keep revolving around that, and this is in fact a three-dimensional object you got at the end. And this is slightly different from what we got in the previous case, right? So we had a totally different, we had in fact slightly different version in the picture as you see. So, but right now we're trying to find a volume of this one. Okay, this one. So to be able to do that, I'm going to go back to that picture and see what the inner and outer radii look like for the slice that I picked here. Okay, so let me just clean this up so that you can actually see that better. Okay, so let's say like I still have the thickness dx, and I still have, let's say, the distance of the slice to the origin to be x. Okay, so let's see what the inner radius is. So the inner radius is in fact this distance here, and the outer radius is this distance here. So I'm going to call this to be little r, and I'm going to call this guy to be capital R. Okay. So let's see what it is determined by. First off, this distance from here to here is always 1, and that's sort of like fixed through the region. Okay, no matter what slice you pick, even for this slice here, right, that distance is always 1. Okay, and I know that this part here, so this distance from here to here, which is the distance from the x-axis to the bottom of the slice, okay, is determined by the purple curve, okay, which is 4 minus x. Okay, this is 4 minus x. And r mentioned in this problem, I'll just move it to right here, okay, so that you will see that. So r is what? 4 minus x minus 1, which is like 3 minus x. Because 4 minus x is the full distance here, and then there's also this 1 unit distance that you should probably take that out. Okay, so that's 3 minus x. And capital R, let's check what it is. So this top portion of the slice, right, top portion of the slice is determined by the blue curve, which is 4 minus 2x minus x squared. Again, this changes depending on what x you are at, what slice you are talking about. Okay, and then we still have to subtract that 1 unit to be able to come up with capital R. So it's 3 plus 2x minus x squared. Okay, for my representative slice, capital R is 3 minus 2x minus x squared, and little r is in fact 3 minus x. Okay, so what I'm going to do now is to use the formula that I have. So the formula is in fact the volume of the outer disk minus the volume of the inner disk. Okay, so that's what I'm gonna. So like, oops, I'm sorry. What I'm gonna do next. Okay, here we go. So the volume, I'm gonna use a different color here, is pi times capital R squared minus little r squared dx. Okay, so pi capital R squared dx is the volume of the outer disk, and pi little r squared dx is the volume of the inner disk. And if you subtract, then that's exactly the formula you get. And I know that x's in the region range from 0 to 3, right? From 0 to 3. So that means the limits of the integral here would be 0 and 3. Okay, so let's just try to write it explicitly. So 4 plus, well, this time capital R was, remember, 3 plus 2x, right? 3 plus 2x minus x squared minus 3 minus x squared dx. Let me just rewrite here. 3 plus 2x minus x squared, and then 3 minus x. Okay? All right. So I think I did this calculation, similar calculation earlier, and I'm going to leave it to you. I'm going to just expand the integrand out, and then please pause the video and convince yourself. This is x to the 4th minus 4 x cubed minus 3x squared plus 18x dx. Okay? And we can use the power rule for integration to find the antiderivative of this. Okay? For the lower limit to be 0, upper limit to be 3. Okay? And right now, please pause the video and plug in 3 for x and plug in 0 for x. But when you plug in 0 for x, you're going to get 0 all the way. So when you plug in 3, you get, let me just continue from right here, right from the top, right here. So it's going to be 108 pi divided by 5. Okay? All right. So when you go back here, so the volume of this three-dimensional object, remember that you just take the volume of the cone because the inner disk, when you combine them throughout the region that makes up a cone, you just take it out of the volume. So volume is going to be 108 pi divided by 5. Please check my calculation and do this, do the calculations by yourself, okay? But make sure like you get the right number out. All right, so I think this takes care of part B, and that this makes it the end of the video. Thanks for watching. I'll see you in another video. Bye.